Good afternoon, everyone. My name is Sam Seifert. I'm a software engineer at Boston Dynamics, and today I have the pleasure of talking to you about Spot Autonomy. That brings us to our first slide. What is Spot Autonomy? I like to think of all the software on Spot as a pyramid, and each individual piece of software is a block in that pyramid. And at the top of that pyramid is Autowalk. Autowalk is a piece of software that ships with the Android tablet app. It is built on top of two services that run on board the robot, GraphNav and Missions. These three pieces of software together combine to form the Spot Autonomy group. Underneath all these pieces of software, there are more pieces of software that aren't part of the Spot Autonomy group, but they're leveraged by GraphNav and Missions. So for those of you unfamiliar with Autowalk, let me give you a brief introduction. A lot of our customers are interested in removing the operator from the loop. They want to use Spot to autonomously go around their sites and perform a bunch of actions. Autowalk is a tool that we've built to help facilitate this. In Autowalk, there's a two-step process that you can do to actually automate the tasks that you want Spot to do. The first step is a recording process. So you're going to manually drive the robot around your site. You're going to perform a bunch of actions. And what's going to happen is the robot is going to create a file that contains all of the information it needs to replay that path and those actions in that environment. You're going to download them to the tablet, and then at any time in the future, you'll be able to drive the robot around, decide that you want to execute one of these walks, select which one walk you want to execute, upload it to the robot, and then run it autonomously. So in this video on the right, there's actually no driver. Spot is driving itself. So today, I really want to talk about how Autowalk works under the hood. And to do this, I got to first explain to you how GraphNav works and how the mission service works. And I think this story is best told from the ground up. There's a lot of pieces of software on Spot. Some of them do very similar things, and I would like to make it clear to you which pieces of software are responsible for what roles, and that way they're all sort of tools in your tool belt that you know how to use most efficiently. All right, so we're going to start with GraphNav. I have been hanging out with my parents a lot recently because of COVID, and I showed Autowalk to my mom, and I asked her, "Mom, how does this work?" And she looked at it for about a minute, and she said, "Well, Sam, it's quite simple. The robot counts steps, and then you build a script, and then at playback time, you just redo those steps." And she's wrong. GraphNav is more complicated than that, but she's not that wrong. It's pretty much just this. And I don't know, I thought it was awesome that she nailed it like that. So what are we going to do? We're going to drive Spot through the environment, and we're going to build this script. What that actually means is instead of counting steps, what we actually do is we pull the frame coming off of the robot's odometry system. So the robot has a system on board that calculates its position since startup. So what happens is when the robot boots, the robot starts at the origin of some grid. And as you walk it around the world through that grid, the robot's position updates on that grid. And we can pull that position and we can save it in a big list of positions and we can play them back. The odometry system spits out information that's available to users of the API through the frame transform odom body. If you were to actually implement this system in this way, what you would find is that initially, when you line the robot up and you start to play back the path that you recorded, you're going to get really good results. Okay? The path that you take at record time is going to match really well with the path that you took at playback time. But as the path length increases and as time goes on, you're going to notice that the paths start to slowly diverge. And the amount of divergence increases over time. And there's an engineering term for this. This is called bad. And we don't want this to happen. And for example, if there was a doorway that Spot was supposed to go through, maybe the drift is so bad that it can't actually make it through the doorway. So why does the odometry system drift? If I took you out into a field and blindfolded you and asked you to walk straight across the field, you probably can't walk straight across. And there's a bunch of reasons for that. Maybe there's some, sensor noise where you think you're walking straight, but you're not actually walking straight because one of your strides is a little bit longer than the other. And you can't really measure that. Maybe it's model imperfections. So maybe our model of our walking behavior is not as accurate as we want it to be. And maybe your feet slip, right? Maybe the robot is on gravel or sand or some other slippery surface. And in those cases, it's really hard to know how the robot is moving through the world because of all the noise associated with slipping. There's a second system on board the robot called the visual odometry system. It includes information coming from the robot's cameras in its update of the robot's estimate of its position in the world. That system drifts less, but it still drifts. And that means that it's not good enough for our use case, right? We wanted the system to not drift at all. We want to be able to play back the path that we recorded identically. So I hope that I've convinced you that just recording a path through the world isn't good enough. To make the problem solvable, you need to add some extra information. And what we do is we actually say every fourth step that the robot takes is special. And at every fourth step, we drop a waypoint. And what happens is that each waypoint, the robot takes a bunch of pictures. As you know, the Spot robot has a lot of cameras on board that gives it almost a 360-degree field of view. Then at playback time, we take the route, we take all of the pictures that we took on that route, and we upload them to the robot. And we ask the robot to start replaying that route. Every time we cross a waypoint, the robot takes another set of pictures. And it compares the set of pictures that it takes at record time to the pictures that it took at playback time. And what it's looking for is it's looking for differences. So for example, maybe in this route path that we've recorded, at playback time, the banana is closer to the carpet. The robot can calculate that and it can make an adjustment. So it can say, hey, I think that I should be closer to the carpet than I am right now. And so what it'll do is it'll move to where it thinks the right position is. And it keeps doing this at every waypoint on the path. And as the robot progresses through the world, we do this sort of over and over again. And what happens is, even though the system still drifts, we can account for that drift, we can correct it, and we can make sure that we get to our destination. So that's what GraphNav is. GraphNav is a tool to remember the robot's path through the environment. It's also a way for the robot to play back a remembered path. Armed with that information, let's take a look at the structure of the API. So we represent a path through the world as a graph that consists of waypoints and edges. Okay? Waypoints are spots in the world. They have sensor data associated with them, and edges connect them all together. GraphNav runs on board the robot, and there are several different methods that clients can call to interact with GraphNav. First and foremost is clear graph. So you can tell GraphNav, hey, whatever path that you're currently thinking about, forget it. The next set of methods that you can call is upload and download graph. So after the robot records a path through the world, you can download it to your client and store it indefinitely. Or when you're ready to replay your path, you can upload that path to the robot. There's also a set and get localization command that you can send to the robot. Get localization is pretty straightforward. It returns the robot's estimate of its position on the current path. Set localization is a little bit different. That's how we initialize the robot to the path. There's also a navigate to command and a navigation feedback command. You use the navigate to command to tell GraphNav to take control of the robot and drive the robot around to different waypoints. And you use the navigation feedback to ask the robot, hey, how are you doing on the last navigate to I sent you? And the robot will respond and say, I'm 30% of the way there, or I'm 50% of the way there, or I'm done. There's also the GraphNav recording service, which is how you're going to create maps. There are two states for that service, recording and not recording, and you can explicitly call start and stop recording to toggle between those states. You can also ask the recording service, hey, are you currently recording? And you can also explicitly tell the recording service to create a waypoint right here where the robot is standing. GraphNav is not perfect, and I want to talk to you a little bit about some of the imperfections of the system, and in an effort to, A, not oversell you on the system, but B, to let you know what some of the problems you might encounter are and how you can overcome them. Confession number one. We haven't really talked about initialization yet at all during this talk. Initialization is the process of uploading a map that you took 3 weeks ago and telling the robot where it is on that map. We have a bunch of ways to do this, but the way that we found to be most effective is to use a fiducial. A fiducial really helps us narrow down our search space. So if you recorded a map that was 1 kilometer long, if we use a fiducial, we don't have to search the entire kilometer to figure out where the robot is. We can just search the 2 or 3 meters in front of that fiducial. This makes the problem a lot easier. Without the fiducial, there are some environments that we really probably couldn't solve this problem. Those are environments that are self-replicative. So for example, a building with 3 identical floors. Without a fiducial, the robot can't really know what floor it's on. Or environments that are bland. Large white hallways, big open rooms. Spot really struggles to know where it is in those spaces without a fiducial. Confession number 2. We never actually solved drift. We just learned to live with it. If you took Spot and recorded a map that you know to be perfectly square because you ended and started at the same place, GraphNav isn't going to necessarily spit out a map that's perfectly square. It could spit out a map that looks like this, or like this, or like this. And this is actually okay. GraphNav can totally account for this. And the only thing that's alarming is that when you look at it as a human, you're like, wow, that doesn't look like the map that I recorded. We agree with you, it doesn't, but the system will still work. So one of the things that you've probably assumed is that when GraphNav goes to localize against the path that you recorded, it looks at features that are geometrically close to where the robot thinks it is, right? It's going to look at features that are nearby because those are the features that are most likely to be seen. And what you're going to also assume is that, hey, when the map doesn't match what's in the world, the robot's going to be confused. It's going to get to the end of the path, and it's going to see that the banana and the tree are really close. And when it compares that to its map, it's going to say, hey, in my map, the banana and the tree are much farther away. I can't rectify this problem. I must be lost, and I'm going to complain. Okay? That's not actually how the system works. The system not only localizes to features that are close to it geometrically, but also along this special axis, this imaginary axis that we created called time or path length. So what does that look like? So when we add features to the path, not only are we going to add them where they are in the world, we're also going to tag them with a path length. Path length here is represented by the color of the path. So the black part of the path is the start, and all the features that you record at the start of the path are going to be black. When the robot gets to the end of the path, what it's going to do is it's going to resave those same features again at a different geometric position and a different path length. What this allows us to do is at playback time, when we go to localize, we are localizing to the features that we recorded when we were back at that region, which means that even if the system drifts, we have multiple copies of the same feature in the map, and we can just localize to the ones that were recorded when the robot was actually at this position in the map, not at the ones that where the robot was at the position at the start of the map. Confession number 3, the graphs don't last forever. Eventually your graph will expire. Sometimes the world changes and the robot can no longer localize and your robot will continuously report lost. Sometimes there's a blockage that's preventing the robot from getting where it needs to go. There are 3 different types of blockages that can happen. First is a small blockage, something about the size of a trash can. In those cases, GraphNav will actually automatically route the robot around the blockage. The second set of cases is where there's a slightly bigger obstacle, something like a car or a forklift. In those cases, GraphNav is going to be really cautious. It won't automatically drive the robot around the obstacle, but if you, the operator, see the robot get stuck behind an obstacle of this size, you can actually manually drive around the obstacle itself, resume your mission, and everything should work as intended. So there is some level of size of obstacles where the robot can't navigate around it itself that you can, and if you do this, you're going to make your maps last a lot longer. Eventually, though, the obstacles get too big and this technique doesn't work, and you just have to re-record your map. Confession number 4. The base platform Spot robot has a very small sensor range. It's about 4 meters. For a lot of environments, this is great. This is totally going to work. Things like office buildings or residential areas or commercial areas that are really tightly packed. It's not going to work well in rooms that are large and bland, like big white rooms or long white hallways. It's also not going to work well in rooms that don't have a lot of features because there's just large open spaces that dominate the geometry. If you find yourself in either of those 2 cases, you have 2 options. Option number 1 is purchase a LiDAR. We sell a integrated LiDAR payload that when plugged into the robot and configured correctly, automatically integrates with GraphNav. And what you're doing here is you're increasing your sensor range from around 4 meters to dozens of meters. So suddenly these large open spaces become navigable. The second option that you have is to paste a bunch of fiducials around your site. In 2.1, there's a new feature that allows the Spot robot to hop from fiducial to fiducial to make its way around areas that otherwise wouldn't have a lot of features. And that's GraphNav. Now let's pivot to talking about missions and the mission service. So you recorded a map of your environment, and GraphNav allowed you to navigate through that map. But that's not good enough, right? We don't want to just go places. We want to go places and take actions. We want to go places and record a bunch of data, take a picture, spin a valve. There are a couple ways that you can do this, okay? The first way is just using the Spot SDK. You can write a Python script that coordinates high-level robot behavior. We found that this does work, but at some point, this becomes very, very cumbersome to sort of perform and to maintain. So what does that mean? If I record a map of my site and I make the perfect Python script to execute my mission on that site, and then 2 weeks later, I record the map again, my mission isn't going to apply to that map, all right? The localizations are going to be different. The waypoints are going to be different. I need to remake my mission. That's a lot of work, and it's cumbersome and tiresome, and you don't want to do it. And our customers don't want to do it, right? If we told the site manager that to leverage GraphNav, they had to write a Python script and debug that Python script, they're not going to be happy, right? They want the system to just work. And that's where the missions and mission service come in. Missions is a high-level robot programming language for coordinating autonomous behavior. The mission service on Spot provides the robot the capability to execute a mission written in that language. Maybe after hearing this, you're thinking, I don't want to learn another language. And that's totally fair, and we recognize that. So instead of making our own special language that you've never heard of before, what we really did is we took behavior trees, something that exists already in literature and you might be familiar with, and we implemented one. And that's what missions really is. It's a formalized behavior tree. There are a lot of resources to learn behavior trees out there, and we think that this is going to be something that all of you guys can do. From personal experience, I can tell you that coordinating high-level behavior is much easier when you create a mission. In Spot 114, Autowalk barely used the mission service. There was a big state machine on the robot, or on the tablet that we had to keep track of, and we managed all of the handoffs between the high-level behaviors ourselves. That was really painful and was really error-prone, and there were a lot of bugs. When we switched to using the mission service in Spot 2.0, that process got a whole lot easier, and it made our lives a lot easier. So I think that the mission service is going to be worth your time to learn. At the same time, if you don't want to learn it, the missions and the Spot Python SDK are both feature complete, so whatever you can do with missions, you can do with the Spot SDK. So let's take a look at the mission service. Unlike GraphNav, there's no notion of recording a mission. You're responsible as a client for creating your own missions and uploading them to the robot. Once you do, you can play, pause, or restart them. You can also ask the mission service, hey, how are you doing with this mission? And the mission service will say, I'm halfway done, or I'm all the way there. I do want to give a brief introduction to behavior trees and specifically our implementation of them. Missions consist of a bunch of nodes. It's actually a hierarchy of nodes. Nodes are tiny reusable blocks that you can use to construct high-level behavior. Nodes get uploaded to the robot and then they get run. And when a node is run, it can return one of three things. It can return success, which means the node is finished and it worked. It can return failure, which means the node is finished and it didn't work. Or it can return running, which means I need more time and I should be ticked again. Every time a node is run, it's called a tick. So let me give you some examples of some simple nodes. So the simplest node is always succeed. Every time this node gets ticked, it just returns success right away. A slightly more complicated node is the sleep node or the wait node. And that node has a parameter, which is the amount of time that you want the robot to wait for. This node will return running until the amount of time that you've specified in the parameter passes, at which point it will return success. Okay? There's also nodes that actually do useful things, like navigate to. This node is what ties the missions and mission service to GraphNav. So you can build a mission that calls GraphNav using the navigate to node. And what navigate to specifies is a waypoint that you want the robot to go to in the world. So that could be go to boiler room A or boiler room B. The mission service will tell GraphNav to go to that location, and it will wait until GraphNav says it's at that location or GraphNav gives up. There are also a lot of nodes that have hierarchy, and these nodes have children. And the two I want to talk to you about today are sequence and parallel. Sequence is going to be your bread and butter if you're using the mission service. A lot of the things that we want to do are sequences, right? Go here, take a picture. Go here, look up, take a picture. Sequence is how you're going to do that. So a sequence can have any number of children, and it's going to execute its children in order until all the children complete. If a single child fails, the sequence itself will fail. The next node I want to talk about is parallel. Parallel node is, again, a pretty simple idea. It's, hey, I want you to do this, but while you're doing this, I also want you to do this. So for example, I want you to take a high-resolution laser scan of this room, and while you're doing that, please stand at full height. That's really where the parallel node comes in. So let's look at an example mission. Our root node is going to be a sequence. Okay? The very first thing that this mission is going to do is going to tell the robot to go to the first waypoint in the map that you've recorded. Then it's going to tell the robot to go to a special waypoint, a waypoint that you want to take a picture at. Once at that waypoint, the mission is going to command the robot to stand at full height. Once the robot is finished standing at full height, it's going to enter this parallel node. And the parallel node is going to tell the robot to take a picture while also telling the robot to stand at full height. And the stand with full height is nested in a repeat forever block. So stand with full height will return as soon as the robot is at its target pose. And what the repeat forever does is it makes sure that that command is repeatedly reissued so that the robot doesn't, lose its lease or think it should be doing something else. Okay? Once the take picture is complete, the parallel node will complete. Once the parallel node is complete, the mission will advance to the last waypoint in the sequence, which is a navigate to the last waypoint in the graph. And you can imagine that you could daisy chain together a bunch of these nodes to make much more complicated behavior than just go to one place and take a picture. You could go to 10 places and take 10 pictures or do a laser scan or whatever other nodes are available to you. Now let's talk about Autowalk. Autowalk is a polished UI built on top of the GraphNav and mission services. Most of the heavy lifting is done by the software on the robot, and Autowalk's responsibility is to coordinate behavior between those two pieces of software. So let's go back to where we started and actually look at what's happening when the user records a map. So Autowalk starts by clearing the graph and then telling GraphNav to start recording. As the operator drives through the world, the tablet really doesn't do much. It just relays those commands to the robot, and the robot moves to the world, and GraphNav is automatically dropping waypoints and creating edges. When you get to a point in the world where you want to perform an action, what Autowalk does is it pops up a UI that allows you to configure your action. So you can stand the robot at an interesting pose while you take your picture to make sure you get, your target in your field of view. Once that's done, Autowalk tells GraphNav to create a waypoint, and then we continue recording. Once the map is recorded, Autowalk tells GraphNav to stop recording and then downloads the full graph. And then it builds a mission from all of the things that you did while you were recording. So the first part of the mission is go to the first waypoint, then it's every action that you did during the mission, and then it's go to the last waypoint. At load time, Autowalk's responsibilities are show the user what walks are available on the tablet, let the user select a walk, give a preview of what that walk is going to look like, and then upload it to the robot. Once the walk is uploaded to the robot, Autowalk forces the user to initialize, and we make you do that using a fiducial, just because, again, we found that to be the easiest and highest chance of success. Once the map is uploaded and the robot has localized the map, we upload the mission, and then we start the mission. And all that's happening here is Autowalk is telling the mission service to continue running the mission. And the mission service is delegating control of the robot to a bunch of different other services and coordinating the high-level behavior. And that's really what I think the value out of the mission service is that if you write a valid mission program, all that you have to do to leverage all of the complexity of that program is just tell the program to run. And the mission service will take care of the rest. And that's it. So what did we talk about today? GraphNav. GraphNav is a way to remember the robot's path through the world and to play that path back. Missions. Missions is a high-level programming language that the robot can execute. Autowalk is a polished UI built on top of the missions and GraphNav services. So what should you do now? So hopefully after watching this talk, you've become a better Autowalk user. You understand how things can fail and what you can do when they fail. If your robot's getting lost a lot, buy a LiDAR, put a bunch of fiducials up. If your robot's getting stuck, manually drive the robot around the obstacle before resuming your mission. Maybe after watching this talk, you're thinking to yourself, Autowalk is great, but it's not for me. I want to develop my own application on top of GraphNav and missions. That's great. We will support you to do that. Both GraphNav and missions services are going to exist long-term on the robot, and we're going to constantly improve them. And maybe you're thinking to yourself, I want to become a part of the Autowalk ecosystem. So to do that, there's two ways. One is by integrating with the data acquisition service, and the other is by implementing a custom callback. All right. That's it, everybody. Thank you so much for coming, and I can't wait to see you all next year.